Okay, so we've got a problem here with a kind of like a, historical battle with a huge wall, and on top of this wall there is a cannon, and the cannon shoots a cannonball. Okay, so we'll say mass of the ball, there's the ball, is 225. Actually, no, the cannon is 225 kilograms. So we'll say mass of the cannon is 225 kilograms. So that's that guy. And the mass of the ball is not, that's wrong. The mass of the ball is, let's see here, 4.5 kilograms. That makes more sense. And when the cannon is shot, it's shot horizontally. Okay, so we know that the original velocity is horizontal. And we know that the ball hits the ground 215 meters from the base of the tower. So the ball basically does this, parabolic trajectory, and well, it's not a very straight line, but you get the idea. It says that it hits at 215 meters from the base. It says that the cannon is also on frictionless wheels, and it falls back and lands on the ground. So basically, when the cannon shoots, the ball goes forward 215 meters on the ground, but the cannon also, I don't think it's going to go as far because it's heavier, it has more mass. And the question is, we don't know this distance. The problem says, what is the horizontal distance of the cannon's landing measured from the base of the back of the tower? Now you can assume that this tower, the horizontal distance of this is insignificant. In this case, I've drawn it to be able to draw the cannon on top of it, but it's not going to have any significant width to it. So at least it's not important for our problem. So how do we find this value x? Well, one of the first things that we need to realize is that this is an explosion. Okay, so let's write down our conservation of momentum. And I can say initially there is no momentum. Nothing is moving before the cannon fires. And then afterwards, we have the mass of the cannon times the velocity of the cannon plus the mass of the ball times the velocity of the ball. Okay? And so we know that they're both going to have equal and opposite momenta. Now, the difficult part here is that we don't really know the velocity of the ball. So let's think of it in this term. Let's think of it in terms of projectile terms. Let's move this up a bit, and let's say to ourselves, okay, how can we use this piece of information? Well, in what type of an equation would that appear? Well, that horizontal distance, let's call it dx, is equal to vx times t. And vx in this case is that, because you see the horizontal velocity with which the cannon is shot doesn't change. It doesn't change because gravity doesn't act horizontally. So now that we know that, we can say, all right, well, that's all fair. I mean, if we knew Vx, then we know that Vx must be this velocity here, right? So this is also the same as Vx. And we can work this out. The problem is now, although we have the horizontal distance, We don't have the time. Okay? But let's see if we can solve for this horizontal velocity in terms of time. And the reason I say that is because let's just go like this, divided by t. Now we have it in terms of the time. Now what time is that? That's the time in the air. Okay? Now if you think back to your projectile unit, it doesn't matter how fast the projectile is shot horizontally from a certain height, it's always going to reach the ground at the same time. If you remember, the classic example of that is you shoot a gun horizontally and the bullet reaches the ground whether it's dropped from the height of the gun or whether it's shot out from the gun horizontally. Therefore, you know that T air for the cannon and T air for the cannonball to reach the ground is going to be the same. Okay? So what we've found here now is that the horizontal velocity, this I'm using an x here, but understand that's for the cannonball. So I'm going to rewrite this equation and say v ball is equal to 215 divided by t air. Okay? And what about the velocity of, not the ball now, but the cannon? That can also be discovered with the same equation, except this time we don't know the 215, we just know that it's x divided by t air. Now we can go back to our original equation for conservation of momentum and take this equation, let's rewrite it down here, and let's write it again, but let's write it like this. Negative mcvc is equal to mbvb. And now let's actually substitute in some things that we know. For example, vc is simply x over t air. And vb is simply 215 all over t air. Now you see where I'm going with this. Now I have, because I know both masses, and I only have one unknown in this equation, I can solve for it. And I'm going to be solving for t air. Okay? Once I get t air, I can work myself back and solve whatever I need to solve for and finish the problem. So right now I want to know the time in the air. How am I going to do this? Well, let's take a look at the math here, and we could cross multiply, or we could, now wait a minute, we can't solve for t air because we don't know x. But we know that t air is the same. Sorry, my math decisions were incorrect. Let's just multiply both these sides by t air, and t air disappears. Okay? And now we've got negative mcx. Still the right track, just the wrong idea. And times 215. Okay? And now we can solve for x. And for x, we're going to get mb all over negative mc times 215. Now that's going to give us mb, I think, was 4.5, mass of the ball, and 225 and 215. I'm not putting in units, which isn't so great, but let's see what we get here. 4.5, enter, 225 divided by 215 times, and I'm getting 4.3, and that's meters. Okay, because that's kilograms, kilograms, and that's meters. Okay, so kilograms cancel out. Now, if we go back, now we know that this distance was 4.3 meters. And that's what we were looking for originally. Okay? And that's the end of this problem. Thanks for watching.